on to the isomer, the new chapter, very important chapter for the midterm range, right? The arcane is a basic stuff, right? So we don't cover up the details of the reactions. We'll learn the reaction of the arcane in the next chapter. This is basically the introductory chapter. So it's the easy one. So if we can cover up 1 to 4, basically 5 is being easy chapter, then you can prepare the midterm. So I've uploaded all the lecture notes, so you guys can preview if you want for the midterm range. So I guess uploaded like till lecture 12 or so, right? Let's cover up chapter 1 through 5. Okay, and then the homework set number 1 will be uploaded April 16th. Okay, so you're gonna have, sorry, actually April. So you need 2 weeks basically. So April 12th, your homework set are gonna be uploaded, so you guys can have 2 weeks to solve the problem. Okay. So the homework set are going to be the last year's midterm exam, so you guys can get a sense of how the exam is going to be. Okay. With that, we can keep going. We'll discuss the conformation isomers. So last time, I guess we stopped here after finishing up the ethane and its conformational state, its complement, right? And you learn how to draw the Newman projections, right? So with the given Newman projection, you guys can get a sense of like a 3D arrangement of the molecule. So you can rotate the methyl moieties, right, respect to maybe the front carbon here. So front carbon is fixed. And you can think about rotating the backward methyl group 60 degrees for each ton. Okay, so from 0 degree, you can assume here start with this conformal state. Right? All hydrogens are basically eclipsed. And then if you rotate 60 degrees, the backward part, right? Then you can draw the Newman projection, right? The backward moieties here. 3 hydrogens rotate 60 degrees all together, right? Which will give rise to the conforming state, which is B, right? And then you can imagine this can go and on, right? 60 degree ton will give you C from B, right? And D from C, right? And if you make 6 ton, right? Meaning 360 degree rotation will give you the initial state back, right? So G here, the conforming state G has to be equal to the conforming state of A, right? This is the simplest case, right? Ethane. And from these, you can identify a pattern such that B, D, F conforming state, they are the staggered conformers, right? They are identical. Whereas conforming state A, C, E, these states are most unstable. These are identical as well, right? And these arise every 60 degree rotation. Okay. And we define the name for the conformer. The left hand side is staggered conformer, right? And right hand side is eclipsed conformer. Pretty straightforward, right? As the name refers to. You can imagine the hydrogen, the carbon to hydrogen bonds are eclipsed. In this case, there are 3 pairs eclipsed, right? And in this case, right, there is no eclipsed CH bonds. They are staggered, right? 그래서 가장 간단한 케이스에 대해서 지난 시간에 컨포머가 무엇인지, 컨포밍 스테이트가 무엇인지, 뉴먼 프로젝션을 어떻게 표현할 수 있는지 배웠었고요. 이제 이거를 응용할 수가 있겠죠. 그리고 조금 더 복잡한 분자로 넘어가서 싱글 번드 기준 하나를 잡고 60도를 돌렸을 때 어떤 컨포밍 스테이트가 나타나는지 저희가 살펴볼 수 있겠습니다. Okay, so again, this is the most simplest case, right? Simplest case for ethane, right? And then we discuss the energetics, right? Why staggered conformer is more stable than eclipsed one, and there are fundamental reasons. And we discuss about the torsional strain, what is the bond-wise overlap, right? So if you seeing the eclipse conformer, right? The ethane, so you can imagine this is a hydrogen. You have hydrogen there, and this is the carbon, right? So you are seeing the ethane molecule eclipse conformer of ethane from side view, okay? You can identify there's a bond between carbon and hydrogen, and there must be a bonding electron occupied the bonding electron, right? If they are too close, right, then you can imagine there is a repulsion between these two. That is the torsional strain or eclipsing strain arising by the bond-wise overlap. Okay, and this can be compared with the steric strain. Okay, this is the atom-wise overlap. So you can imagine you have carbon here and there, and hydrogen. And you have methyl moieties in this case. Okay, so this is basically a CC bond here and there, and you have hydrogen, right, here and there as well. And if they are close each other, too close, then they can repel to each other. This is atomistic or atom-wise overlap, and we define this strain as steric strain. Okay, so origins might be similar. If electrons are too close, they start to repel, right? But you can see the difference, right? This is the bonding electron, they can repel. In this case, right, the atom-wise repulsion. Okay, and this is the case for the eclipse conformer. And we also discussed about the hyperconjugation effect. Okay, so hyperconjugation is basically delocalization of electron by overlapping overlap of sigma orbital with an empty orbital. Right? So we take this example. So this is again side view for the staggered conformer of ethane. So you can imagine there is a bond, right? Bond between carbon and hydrogen here and there. Okay? So you can imagine then there must be a bonding orbital between carbon and hydrogen. Okay? But in this case, your bonding is here, right? So you can imagine then the opposite side, there's a sigma anti-bonding orbital reside, which is empty. Right? And these two now can talk to each other. They can conjugate it. They can share the space so as to delocalize the electron in the bonding orbital, right? For the larger space, which eventually decreases the energetics of the system. Because electron can delocalize, right? So they can decrease the repelling energy, the negative energy. Okay? That's how the hyperconjugation can decrease the energetics of the system. In other words, the molecule can become more stabilized. Okay? So here you can rationalize that stabilizing interaction between CH sigma bond, okay, or sigma bonding MO, and CH sigma anti-bonding MO. Okay? 그래서 하이퍼컨주게이션이라는 컨셉이 이제 유기화학 공부하다 보면은 종종 나올 텐데, 뭐 기본적인 아이디어는 일렉트론이 좁은 스페이스에 너무 갇혀 있으면 서로 리펠링하기 때문에 electrostatic destabilization 일어나게 되겠죠. 일렉트론이 조금 넓은 공간에 delocalization 되고 넓게 퍼질 수 있는 환경이 혹은 효과가 조성이 된다면 에너제틱 관점에서 이제 안정화되는 효과가 있을 수 있다. 그것을 받아들이실 수 있다면 이 경우에 시그마 번딩 일렉트론이 시그마 엔타이 번딩 오비탈과 패러럴하게 놓여질 수 있는 상황이 생기게 되면 이 사이드 투 사이드 인터랙션이 가능하게 돼서 이제 비편제화, 디로컬라이제이션이 되게 되겠죠. 이러한 현상을 저희가 일반적으로 하이퍼컨주게이션이라고 부릅니다. 대부분의 경우 필드 오비탈, 언필드 오비탈이 위치적으로 가깝게 컨주게이션 될 수 있는 위치가 만족이 된다면 현상이다. 이렇게 이해하시면 되겠습니다. 그러면 이제 하이퍼컨주게이션 효과와 앞에서 저희가 정의한 스트링 효과 두 개가 더해져서 이클립스 컨포머가 스태거 컨포머보다 불안정하다. 이제 그 두 가지 효과로부터 설명할 수 있게 되겠죠. Okay, so we discussed right eclipse or torsion strain, right, and also the hyperconjugation effect from these two, you can rationalize why this staggered conformer is more stable than eclipse conformer. So here you can rationalize the eclipse conformer case. You can expect there is a torsional strain, right? You can see each bond. Right? There's no hyperconjugation stabilization effect. Right? So this is again the side view of the ethane molecule. Okay? The bonding orbitals there, here, and there, and anti-bonding orbitals are sitting here and there. If this is anti-bonding orbital, this is CH bonding orbitals. They are too far, so you cannot expect to accommodate the desirable amount of the hyperconjugation, right? So weakened hyperconjugation plus the Pauli exchange, which means repulsive interaction between the bonding orbital. That's basically the torsional strain as we discussed and defined. Okay? So from these two effects, you can imagine the eclipse conformer would have higher potential energy, which means unstable. Whereas the staggered conformer can accommodate the hyperconjugation, as we discussed in the previous slide, and also there is no torsional strain. There is no bonding electron overlap in this case. Okay? So from these two reasons, staggered conformer would have lower potential energy and more stable. Okay. And this is the free energy diagram, or potential energy surface, a function of the rotation, right? Then you can imagine, right, this kind of like periodic trend or rise. And you can identify perhaps the energy maximum for the eclipse conformer, okay? And also the energy minima for the staggered conformer. Okay, and there is a value here, 12 kilojoule per mole. That's the barrier for the staggered conformer. Staggered conformer to the eclipse conformer. Energy difference between staggered and eclipse conformer. Right. So this is the barrier. So in order to this conformer goes to this conformer, you need to overcome this kinetic. Okay, but this is tiny of energy. So you can imagine then under room temperature, for instance, the thermal energy is enough to provide the energy, right, for this staggered conformer can go from here to there, right? And I guess this is the number of frequency, the millions of times per second, right? So they can go forward and backward, right? Very, very quickly, because the room temperature is sufficient to overcome this kinetic barrier. All right, that was the ethane case, and we can move on to more complicated case, right? With the butane, right? So this is the butane molecule containing 4 carbons, right? And then you can think about, right, what single bond you should refer to, right, when you draw the Newman projections. In this case, it's better to pick the bond between C2 and C3 carbon, right? And then you are seeing the butane from side this way, right? And then you can imagine this, right? Front carbon will have 1 methyl group. The backward carbon will also have, right, 1 methyl group as well, right? And also the 2 additional hydrogens here and there. So then you can imagine, right? These conformer states can rise. 그래서 부테인의 경우에는 이제 어디를 기준 싱글 본드로 잡냐, 뉴먼 프로젝션을 그리고 컨포밍 스테이트를 모두 표현하는 데 있어서 적합한 이제 싱글 본드를 일단 선택을 하셔야겠죠. 대표님 경우 가운데쯤 형성되어 있는 싱글 본드를 고르시면 되겠죠. 그러면 이 C2와 C3 본드를 이제 돌린다, 회전시킨다라고 했을 때 앞에 카본에 메틸 하나, 수소 2개 달려 있고 뒤에 카본에 마찬가지로 메틸 하나, 수소 2개 달려 있으니까 그걸 감안하셔서 컨포밍 스테이트 하나 그리시고 60도씩 돌리시면 되겠죠. 그러면은 A, 2, F 그리고 마지막 A까지를 모두 그리실 수 있을 거예요. Okay? So you can start from maybe a random point, right? Conforming state of A, eclipse conformer, right? And you can imagine rotating the backward carbon 60 degrees for each, right? Then you can imagine B will arise from A, right? And C will arise from B, and so on. And eventually, after 360-degree ton, you'll get back to A. Okay? And from a similar patterning, you can identify the eclipsed and non-eclipsed complementary state, right, as blue and red box highlighted here. Okay? This is eclipsed. You have also here eclipsed, and eclipsed complement, okay? And you have the non-eclipsed complement B, D, and F as well. Okay? Well, you can identify right here the D, this third or non-eclipsed complement looks different than B and F. B and F are identical. Okay? And there's a special name in this case when methyl close to enough, but they don't eclipse, right? Still staggered, but we call out this B complement state as a Gaussian complement. So B and F are the same Gaussian complement. But if you have the methyl group, right, locating an n-type position, meaning they are locating to opposite direction, right? In this case, we call out this as an n-type complement, right? So again, B and F, these two are same Gaussian complement, but D is the n-type complement. N-type in Greek, of course, opposite, meaning this metal and this metal sitting opposite way. Okay? You can think about the Gaussian complement and their energetics. And this is the side view of the Gaussian complement. And you can perhaps identify these methyls, right? There must be an interaction between these two methyls. They are sitting close enough. And this is the basically steric reversion. And we'll learn about the diaxial interaction or the cyclohexane case. But basically, this is steric strain or steric reversion. But in this case, we specially named Gaussian interaction. Okay? When methyl and methyl, they sit close enough in staggered state. We define this as a Gaussian interaction, and this is about 3.6 kilojoule per mole energy. Okay? And again, B and F have same Gaussian interactions here and there. Again, you have 3.6 kilojoule per mole destabilizations compared to the non-eclipsed, sorry, the staggered complement, more stable and energetic state. We'll see in the next slide. Okay, and again, the steric strain is a strain arising when atomic groups are close enough for the electron clouds to repel each other. Okay. What about the eclipse conformer? You can identify A and C and E here, and perhaps you notice that A and C they doesn't look same, right? Even though they are both eclipsed, whereas C and E they are symmetrical, basically same. They do have two, right? CH and C methyl bond eclipsing interaction, right there, and also one CH-CH eclipsing pair and CH-CH eclipsing pair as well. So essentially, C and E are identical, whereas A, they do have two pairs of CH-CH, right, eclipsing interactions, and also here, that's the special one, right? So methyl eclipsing interaction. So A has to be different from C and E. Right? And here you can imagine the eclipse conformer in which two methyl groups are close to each other, which is A, has to have more or higher in energy, or in other words, less stable than the eclipse conformer in which they are far apart, C and E. So it can be more, perhaps, quantitative, and this is the number, perhaps, better to remember, right? So here we are comparing the eclipse conformer A for butane and eclipse conformer C for butane as well, right? And you already know that one CH-CH eclipsing strain, where in other words torsion strain, gives rise to 4 kilojoule per mole higher in energy, right? So you have 2 pairs of that, right? Which will sum up 8 kilojoule per mole, right? But you have here one more pair between methyl and methyl, where CC bond eclipsing pair, right? Which will give rise to 11 kilojoule per mole destabilization. And this is sort of like the combination of steric and Austrian strain. So if you are seeing, right, these pair from right hand side, right? So you can imagine there's a bond electron overlap, right? This is the C bond here and there, okay? And there's a bonding electron residing here and there, very close enough, giving rise to torsion strain. And also you have one more destabilization factor, right? The atom-wise overlap between these 2 hydrogens. They are sitting too close to give rise to steric strain, or atomistic overlap, or atom-wise overlap. Okay? So the combination of these 2, these portion will give you 11 kilojoule per mole destabilization. So in total, then you can sum up 4 plus 4 plus 11. That will give you 19, right, kilojoule per mole destabilization. That's for A. And we can think about C, the eclipse conforming state C, which are not identical. But A, and you have again CH torsional pair, torsional strain, so it's 4 kilojoule per mole. And here you have CH and CC bond torsional strain, which is around 6 kilojoule per mole, right? Here and there. So sums up, this will give you 4 plus 6 plus 6 is 16 kilojoule per mole. Okay? That's how we can be more quantitative when you compare A versus C or C versus A, right? And this is a side view highlighting the CH and C bond torsion strain, right? You here again carbon here and there, and methyl group, right? And you can imagine that there is a torsion strain or eclipsing strain between these 2 bonding electron pair, right? But these methyl or these hydrogen atoms are sitting too far from these hydrogen, right? So there might be a less or minute steric strain. That's why in this pair, only give you 6 kilojoule per mole compared to this pair, right? You can imagine 5 kilojoule per mole less amount of destabilization, okay? And that is due to the minute steric strain, right? For these pair, but again, for the upward pair, right? You have this scenario, right? So there is a steric strain, so you can imagine why, right? Eventually eclipse component A has a higher energy than C. Okay, and this is quite a simple number you can memorize. So probably better, okay, to remember this number 4, 6, 11. Okay. With that, you can rationalize this free energy diagram. The potential energy of your complements as a function of the diameter angle, which means the rotation angle, right? So from these eclipse complement, right, as you calculate, this is 4, 4, 11, right? So this will give you a 19 kilojoule per mole. And then you have these eclipse complement, C and E, which are identical, which you already know. And you know this is 16 kilojoule per mole. That does is 4, 6, 6. Okay. What about Gaussian complement? We define the Gaussian traction. We'll give you 3.6 kilojoule per mole each energy, right? So the barrier from here to there is 3.6 kilojoule per mole. Of course, the baseline here is a case for D, there's no strain, right? So you are referring to the zero energy from D. Okay, so anti-complement, in this case, the most stable complementary state. Okay. And you know that these complement F is energetically and arrangement-wise identical to B, right? So you have 3.6 kilojoule per mole range. Okay, A is of course identical to A. 그래서 여러분들이 컨퍼밍 스테이트를 다 그리실 수 있고, 그리고 각 컨퍼밍 스테이트의 상대적 에너지 스테이트 비교를 하실 수 있으면 다음과 같은 프리 에너지 다이어그램을 그리실 수 있겠죠. 휴먼 프로젝션 그리고 eclipsing strain 혹은 torsion strain 그리고 steric strain을 구별하셔서 이제 정량적인 센스를 가지고 계시다면 이제 다 그리실 수 있을 겁니다. Right, with what you know, right, you can perhaps try to solve this. This is the pancake case, very similar. If you think it's a practice, you can maybe try to solve. And here's a hint. You can draw the human projection or conformal state based upon C2, C3 rotation. Why don't you take a moment and try to solve this? So this is basically same with the butane case. Here's an answer. I'll note this as well. So you can identify 6 different conforming states. Instead of metal, you can put the ethyl group, right? And maybe 60-degree bond. And then applying the same logic, same quantitative information, you can draw, right, this potential energy diagram as a function of the rotation or diagonal angle. 그렇죠? 그래서 사실 거의 똑같습니다. 이거 업로드 해드릴 테니까 사진 찍고 싶으면 찍으시고. 근데 뷰테인 케이스와 똑같아요. 메틸 대신 에틸만 들어가고 에너제틱 패터닝도 똑같죠. Okay. Right, that was about the conformer or conformer state or confirmation isomer of the alkyl chain. Right? But now we can think about the cycloarcane and conformer state of those species, right? For which you need to think about the angle strain. Okay? So what is the angle strain? Maybe you can perhaps just start to think about, right? The ideally for sp3 carbon is a bond angle of 190.5. Okay? This will give rise to tetrahedral geometry. Right? 190.5 is basically the tetrahedral angle. And Bayer and Olides argue that the stability of the cycloarcane be predicted by the difference between this ideal bond angle, the tetrahedral angle, 109.5 degree, and the bond angle in the planar cycloarcane. So delta, these two will dictate the stability of the cycloarcane. That was the initial argument that Bayer in all of these. Right? So he basically assumed the the planarity of this structure. Okay? So this is the cyclopropane, for instance, butane, pentane, and hexane. Okay? And you can then decide, right, the bond angle of the planar cyclic hydrocarbon. Okay? So he argued based upon, right, these molecules are planar, which are not true. But assuming, right, they are planar, then you can think about the bond angle between these and this is 60, here 90, 108, 120. Okay? So from his argument then, right, cyclopentane has to have the lowest energy. Right? The delta is merely 1.5. Okay? So the deviation from 109.5 causes angle strain, according to his argument. Right? That is the definition of the angle strain, by the way. And these decrease, the deviation decrease the stability. Okay? In other words, increase the energy of the molecule. Okay? But this argument is only valid only if the compound, again, is planar. But again, this is not true. But in early days, they didn't know. Right? They just assumed this structure, this molecule have planar structure. But now we know that cyclohexane, for instance, is not a planar molecule. So you need to think about in 3D picture, right? 3D space. But cyclopropane is truly a planar species. So we can perhaps think about a little bit more about the angle strain within this example. And you know that again, for a strong bond, you need a good overlap between orbital, right? The cyclopropane, for instance, right, has a sp3. So you have each bond here and here, each carbon, right? So if you think about the number of arms, right, this carbon has 4 arms, so it must be sp3 hybridized, right? So these must be the sp3 hybridized orbitals. Okay? You need to, right, accommodate strong bond. These two has to have a large amount of overlap. Right? So A is a good one. But B, right, you can imagine the degree to which, right, these two orbital overlap is quite small. So compared to your A case, this will give you the weak bond. Okay? Applying this to cyclopropane now, then you can imagine the interaction between sp3 orbitals, right? Can be very, very minute. Okay? This is orbital diagrams formulating the CC bonds of the cyclopropane. Okay? You can imagine there's a carbon. And because there's 3 points, right? Define a plane. The carbon of cyclopropane, they also must lie in a plane. And this is the side view with cyclopropane. And also then you can imagine there is an eclipsing interaction between this H and CH bond. Right? There must be a torsional strain involved. Okay? 그래서 사이클로프로페인의 경우에 이제 에너지적으로 앵글 스트레인을 이제 어떻게 설명할 수 있냐, 결국 오비탈 오버랩 정도로 설명을 할 수 있는데 구조적으로 이제 삼각형을 만족해야 되잖아요, 그죠? sp3 하이브리다이즈 오비탈끼리 이제 오버랩이 결국 CC 번들을 형성시키는데 이 역할을 한다라는 프레임워크에서 생각해봤을 때 오버랩이 적다라는 이야기, 당연히 스테이블하지가 않겠죠. 앵글 스트레인이 이제 그런 방식으로 오비탈 띠오리 관점에서 해석이 가능하다라는 거고요. 추가로 또 사이클로프로페인 구조를 이제 보면 CH 페어끼리 이클립싱 스트레인도 있을 수 있다. 그래서 앵글 스트레인과 이클립싱 스트레인 등등이 더해져서 사이클로프로페인 이제 상당히 높은 에너지를 갖게 되겠구나라고 이제 생각을 해보실 수 있겠죠. So 이제 cyclopropane, right, for the perspective of the orbital interaction. In order to impose the triangular geometry, right, you must, right, have this weak interaction between sp3 and sp3 hybridizable, right? So that is basically the angular strain, the origin of the angular strain. Right? You have closer to 109.5 degree, then you can imagine, right, the soil will have this type of interaction, the strong overlap, meaning strong bond, meaning lower energies. On top of that, right, if you think about the geometry of cyclopropane, right, you can imagine there is a eclipsing attraction between this CH and CH bond, the bonding electron-wise overlap. This will give rise to the torsional strain. So from the angle strain and torsional strain, you can expect propane will have very higher energy. Okay? Right, that was the ring strain of the cyclopropane. Okay? But what about the other cycloalkane? Okay? About cyclobutane, cyclopentane, and hexane. Right? They can basically twist and bend out of the planar arrangement. Okay? And the reason for that is to minimize the ring strain. The ring strain can be defined as a sum of the angle strain and torsional strain. Okay? And cyclobutane, pentane, hexane, they can twist and bend, right, to minimize the ring strain. And that's the reason why they can accommodate varieties of conforming states. Okay? And this is our example, the cyclobutane case upward, the cyclopentane case downward. Right? This is one of the conforming states for cyclobutane called the butterfly, for butterfly conformer. So you can draw this bent type conforming state as well. Right? And this is the Newman projection for the bent conforming state. Okay? They still have angle and torsional strain. Okay? You can perhaps identify, right? For instance, here the bent cyclobutane, they do have more angular strain, which is more compensated by a decrease in eclipse hydrogen. Right? So in this case, right, compared to butterfly conforming state, less eclipsing hydrogen, there's less torsional strain, but they do have higher in the angular strain. So there's a compensation. What about cyclopentane? You have the envelope conformer and twist conformer as well. Okay? They are less strained if you're comparing this with the cyclobutane case. Okay? And this is the Newman projection for this twist conformer. What about cyclohexane? Cyclohexane is unique, right? That's why we studied more. Okay? And perhaps you already know the cyclic compound most commonly found in nature, the 6-member ring. So you can perhaps identify the 6-member ring structure a lot in compounds, right? And the reason for that is they can accommodate nearly strain-free chair conforming state. Okay? All the bond angles. So this is the conforming state, the chair conformer of cyclohexane. And with this conforming state, all the bond angles are nearly tetrahedral angle, right? 111 degree, close to the 109.5. All the adjacent bonds are basically staggered. Right? So this is a Newman projection of the chair conformer. Right? You can perhaps draw this. Right? Your eye perhaps locating in appropriate direction, then you can perhaps draw this Newman projection for the chair conformer. Right? And this is the ball and stick model of the chair conformer, basically, right? Same thing. And with this, right, Newman projection and conforming state again, you can avoid all the eclipsing interaction, the torsional strain, and there will be no angle strain as well, right? Meaning all the CC bond is within the 6-member ring have a very large amount of degree overlap. 그래서 텍스트북에서 이제 사이클로헥세인에 대해서 더 많이 배우는 이유가 사이클로헥세인의 경우에는 이런 최고 컨포멀 스테이트를 가짐으로써 스트레인이 거의 없는 이제 아주 안정한 구조를 가질 수 있기 때문에 자연계에서 많이 발견되고 그래서 우리가 많이 공부하는 겁니다. 구조적으로 재밌죠? 이 최고 컨포멀 스테이트, 육각고리 구조인데 최고 컨포멀 스테이트를 가지게 되면 저희가 앞에서 정의한 모든 스트레인으로부터 자유로워질 수가 있다. 이제 여러분들이 설명하시겠으면 좋겠습니다. 제어 컨펌으로부터 뉴먼 프로젝션을 그려보면 이클립싱 인터랙션, 이클립싱 페어가 거의 없는 거를 아실 수가 있죠. 그렇죠? 토션 스트레인은 없구나. 그리고 스트레이트 스트레인도 없구나. 그리고 앵글 스트레인도 없죠. 그렇죠? 번 앵글이 거의 뭐 109.5도에 아주 근접해 있으니 그 말의 의미는 앞에서 저희가 사이클로프로페인인 경우에서 봤듯이 sp3, sp3 하이브리다이즈 오비탈끼리의 인터랙션 혹은 오버랩이 아주 극대화될 수 있는 구조다라고 이제 저희가 또 생각할 수 있겠죠. 결론적으로 스트링으로부터 아주 자유로울 수 있는 특별한 컨포닝 스테이트가 사이클로헥세인 구조에서 나올 수 있고, 그래서 자연계이 많이 등장하게 되고, 그래서 저희가 더 많이 공부하는 거다, 그렇게 이해하시면 되겠습니다. Alright, so perhaps it's better to know how to draw the chair conformer, right? And there's a goal, okay? And this is how you can visualize the cyclohexane as well. Okay? So let's practice. To draw the hexane in its conforming state, especially the chair conformer, you need to follow the direction. So first, you draw the two parallel lines, the same length, slanted upward. You know that in the skeletal representation, you know that it does indicate carbon, and I here indicate the bond between two carbons. Okay? Number two, complete the framework of the six-member ring. Right? So you can basically connect with an inverted V. Okay? This is an inverted V. And you can also connect the top with your normal V. You can perhaps think about this as a chair. Right? So in this depiction, the cyclohexanes build edge on, right? So you can imagine these three carbons, they are sitting front, right? From your perspective. And these three carbons, they are sitting backward. Okay? And then there are two types of carbon you should specify here. Down carbon here, up carbon there, down carbon again, and up carbon again. This is alternated, right? Up, down, up. Okay. So compared to like left and right carbon sitting next to it, you can identify whether this carbon is down or up. Okay. This carbon is up compared to this two carbons. Okay. This carbon is down compared to these two carbons. Okay. And this carbon is down compared to these two carbons sitting next to it. Okay? So 이 퍼스펙티브로 최후 컨펌을 보실 수 있다. 그러면 일단 성공이죠, 그죠? 2D 종이 위에다가 3D 구조를 그리는 거잖아요, 그죠? 이제 이 룰을 따르시고 이 투영된, 이렇게 약속된 이 투영법을 가지고 보시면 이제 체형 형태로 보이시기 시작할 겁니다. 그러면 뭐 등받이, 뭐 발바지 이렇게 생각하시면 되겠죠. 근데 룰이 있다. 사이클헥세인 컨펌을 그리는데 체형 컨펌을 그리는데 룰이 있어서 따르셔야 돼요. 이 문법을. Right. What about the actual bonds? So the six-member ring is now defined, but there might be a case the actual bond exists. Of course, for the cyclohexane, you can imagine there's CH bond, right? Okay. So there's a rule. The up carbons, as we defined, right, have upward actual bonds, okay? And down carbons will have downward actual bond. Okay. So for instance, you know this carbon is up, right? This carbon is also up. This carbon is also up. So for the actual bond for this up carbon, for the actual bond, you need to draw an upward. Okay. So up carbons again have upward actual bonds. That's the rule. What about down carbon? You have down carbon here, here, and here. And each have the actual bond as well in this case, and that must go down. Okay? Down carbon have downward actual bond. Okay? And for the cyclohexane, of course, you can think about there's a CH bond, right? There's one more piece, the equatorial bonds. And there's a rule, okay? You should draw the equatorial bonds pointing outward from the ring. Okay? So from the ring, you should draw the bonds towards the outside. That's why you draw from this carbon or this equatorial hydrogen, right? Pointing outward from the member, 6-member ring. Same is true here, there, here, here, and here. Right? And when you draw this equatorial bond, you should on a slant. Bond angles are not 90 degree, right? It's 110 or 11, right? So you should draw on a slant line. 약간 기울여서 그리셔야 된다는 얘기예요. 원도의 그리 90도가 아니잖아요, 그죠? 그러니까 이렇게 수직으로 그리면 안 된다. 약간 슬랜트를 그리셔서 기울이셔서 그리셔서 110도 정도가 되게 그리셔야 되겠죠, 그죠? Okay, so you should draw the equatorial bond pointing out of the ring on a slant, and there's a rule, additional rule, right? Bonds on up carbon for the equatorial one, this should be downward slant. Okay, so you have, for instance, here the up carbon, and up carbon, right? And you draw the equatorial bond, right? Slightly downward slant, downward slant, downward slant. Okay. For the up carbon, here and there, right? You should draw the equatorial bond slightly upward slant, like this, upward slant. 그래야 90도 각이 커지겠죠. 그렇죠? 원리적으로 당연한 겁니다. 근데 규칙적으로 만들어 놓으시면 따라하실 수 있겠죠. Okay, so in this case, for the cyclohexane case, of course, you can think about there's a hydrogen in CH bond. That's for the equatorial bonds. Okay. Right, that was the rule for the equatorial bonds, and with all this piece, you can draw right the chair conformal. And this is a summary basically, right? So with this right conforming state, you can perhaps identify the nature of carbon, right? You have up carbon, up carbon, right here and there, and you have downward carbon, down carbon, and down carbon. Right? Once you identify the character of carbon, right, and then you can think about the bond, right? The actual bond and the equatorial bond. So up carbon's upside, right? So up carbon's upside is the up actual bond. Also, the up carbon's upside, the up actual bond. But up carbon's downside, right? These are all equatorial bonds. So up carbon's the downside here, it's an equatorial bond. Okay? That's how you can define the side of the ring, upside or downside as well. Okay? Again, up carbon's downside is equatorial bond. What about down carbon? So you have down carbon here. Down carbon's downside is the down actual bond. Okay? So you have this bond, down actual bond, down actual bond, down actual bond. Okay? What about down carbon's upside? That's the equatorial bond. Here, and here. 그렇죠? 그래서 여기에 해당되는 이제 다운, 업, 다운, 업이 주체에 따라서 여러 가지가 나오잖아요. 그렇죠? 요거를 구별해서 이해하시면 되겠습니다. 카본 캐릭터가 업, 다운이 있고 green 캐릭터가 업, 다운이 있고 그죠? 그거를 구별해서 이해하시면 돼요. 업 카본의 업사이드는 업 액츄얼 본드고 업 카본의 다운사이드는 이퀴토리얼 본드. 그렇죠? 다운 카본의 업사이드는 이퀴토리얼 본드고 다운의 다운은 다운 액츄얼 본드. 헷갈리실 수 있는데 좀 그려보시면은 감을 잡으실 거예요. 근데 이렇게 업, 다운 방향성을 구별하실 줄 알면 이제 체어 컨포먼트 마스터하실 수 있겠죠. 그렇죠? 주체가 두 가지다. 카본의 캐릭터가 있고 링의 관점에서 업, 다운 사이드 구별해서 이해하시면 되겠습니다. Right. So with this knowledge, you can think about the interchange between two conformal states, two chair conformal, which is called the ring flip. Right? So cyclohexane ring, they can flip. Right? So cyclohexane, they can rapidly interconverge between two stable chair conformals because of the ease of the rotation about its CC bonds, right? And this conversion is called the ring flip, right? So this conforming state can go to this conforming state, right? And there is a rule when ring flip take place, okay? And it's better to remember this, right? So up carbon basically changes into down carbon after ring flip, and vice versa. The down carbon, they goes to up carbon. Right? That's the rule number one. Right? So that's about the character of carbon and how they change upon the ring flip. And bonding wise, there's an interconversion, right, between equatorial bonds to axial bonds. Right? So every equatorial bonds, they change into the axial bonds and vice versa. Okay? Every axial bonds, they become the equatorial bonds. Right? So you can perhaps, right, compare left and right before and after being flipped and check whether this will apply, right? So every down carbon here, these 3 down carbon, they go up, right? These carbons now go up. Number, right? 4, 2, 6, right? From left hand side, they were down, but the right hand side, they become up. Okay? And you can check 1, 3, 5 as well. On the left hand side, if 1, 3, 5 carbons, they are up carbons, but the right hand side, they become down carbons. Okay? You can also think about the bonds, right? The equatorial bonds, right, all the blue highlighted, right? They become all axial. Okay? 3 of them become up axial, right? And the rest 3, they become down axial. And all the axial bonds, right, it's red triangle, right, they become the all equatorial. Okay, that's the change you should remember before and after ring flip. The character of carbon, they changed, and also the nature of bond, their direction changed from axial to equatorial to axial. If you remember this, then you can draw the ring flip conformal without any error. 그렇죠? 요거를 기억하시고, 그렇죠? 프랙티스를 해보시면 됩니다. 요 룰이 내가 윙플립된 컨포머를 그릴 때 적용이 됐나, 카본의 캐릭터가 업에서 다운으로, 다운에서 업으로 컨버전이 제대로 됐나, 그리고 본드의 캐릭터가 이퀄리티에서 액션으로, 액션에서 이퀄리티로 컨버전이 잘 됐나, 요거를 체크하시면 되겠죠. 체크해 가시면서 이제 열심히 그리시면 됩니다. 그렇죠? Okay. That was about the ring flip, and the reason why we discuss ring flip is the energetically, right? 2 conforming state before and after ring flip, their energetics can be different, right? So we can think about the conformer of monosubstituted cyclohexane, meaning you have one substitute, right? Which is metal in this case, and this is the one chair conformer you can imagine. And after ring flip, right, applying the rule we just discussed in the previous slide, and perhaps now we can draw, right, the ring flip conformer. Okay. So equatorial CC bond now become axial CC bond. Right? This is up carbon, right, the left hand side. After ring flip, this carbon become down carbon. The downs, right, axial has to be down. Right? That's why you have here the down axial bonds, right? Consistent with the rule we just found. Right? And then you can compare the energetics of this chair conformer versus this conformer. And the answer is, right, the left hand side is more stable. This is a more stable chair conformer. The right hand side is less stable chair conformer. And we'll discuss why that's the case in the next slide. Okay? So axial and equatorial substitute, right, they interchange upon the ring flip. Okay, this equatorial position goes to the axial position. But after ring flip, right, this carbon is down. Down's axial is down. That's what you have here, the down axial. 그렇죠? 그래서 애초에 사이클렉스인의 체험 컨펌을 그릴 때 배우셨던 룰과 링 플립 때 배운 룰을 2개를 항상 기억하셔서 적용하시면 이 다운 카본의, 업 카본의 이제 다운 포지션이 이퀄리티라고 배웠죠. 여기 이제 업 액션 C 처음 있는 거고요. 링 플립 이후에 요 CH 액츄얼 번드는 이퀄티얼로 가 있겠죠. 그렇죠? 액츄얼은 이퀄티얼로 가고. 근데 기억하실 것이 윙 플립 이후에 업, 다운 사이드는 이제 변하지 않는다. 이제 기억하시면 되겠죠. 그래서 업 카본의 업 위치는 CH1도 유지가 되는 거고, 다운 카본의 업 역시 업사이드로 유지가 되는 거죠. Okay, so that's how we can rationalize the conforming state after ring flip when you have substituent on the ring. Okay, so side of ring doesn't change, upside, downside, they retain, but the character of carbon change, and also the bonding nature change. Right? So up carbon become down carbon goes up carbon, equatorial bonds go to axial bonds go to equatorial bonds. The side of the ring doesn't change, right? It's a one ring structure. And since we know that left side is a more or lower in energy, right? Energetically, they are not equally partitioned, right? So why equatorial position is energetically stable? This metal is more stable than this metal, and we can understand this from these Newman projections. We still have 10 more minutes. So this is the case of the Newman projection. When you draw the equatorial metal, right? This left-hand side conforming state can be drawn with this Newman projection. And you can perhaps rationalize why this should be the case. Versus right on the right-hand side, you are seeing the conforming state, right, having the metal on the axial side, right? But this is drawn in the upward direction. Okay? So we can compare this to this slide, right? So this metal extends into the space away from the rest of the molecule, right? There is no molecule or atomistic constant, right? Whereas this metal is pointing upward, and there is a nearby hydrogen, right, close to the actual substance of the carbon, basically the same side of the ring, right? And there is interaction between these stabilization effects. If you see, right, it's a different angle with this side view conforming state. You have this upward metal here, and there is a CH bond, right, within this methyl group. And now this hydrogen, right, sitting close enough to the other axial hydrogen, right, and they can repel to each other. And we define this interaction as a 1-3 direct interaction, right? Because you can count this carbon. If this carbon is number 1, then you can identify this carbon as 3, 1, 2, 3, 1, 2, 3. Okay? That's how we define this as a 1-3 diaxial interaction, and the nature of this interaction is this steric repulsion between two hydrogens, and there are two pairs. Okay? So as we just learned the beginning of this lecture, the gauge interaction we defined, right? When metal and metal they are sitting close enough, we define this gauge interaction corresponding to 3.6 kJ per mole of steric repulsion steric strain, right? And this is one pair of the gauge interaction. If you compare this with the 1-3 diaxial interaction we just defined, and you can perhaps think about this as two pairs of the gauge interaction. That's why energetically 7.2 kJ per mole can arise from this 1-3 diaxial interaction. So essentially, right, gauge interaction and this 1-3 diaxial interactions, they are same. Right? The magnitudes are different because for the diaxial interaction, in this case, there are two pairs of the gauge equivalent. 그죠? 본질적으로 같다. 개수만 잘 세시면 됩니다. H와 H 사이에 스테릭 스트레인이 존재한다. 두 개가 이제 가깝게 위치가 되니까. 그래서 메틸이 액션으로 위치하게 되면 메틸에 존재하는 요 하이드로젠과 또 다른 사이클 헥센의 같은 사이드에 있는 CH의 H와의 이제 스테릭 스트레인이 생길 수가 있는 것이고요. 그래서 에너제틱ally 불안정해지겠죠. 본질적으로 앞에서 뷰테인의 경우였죠, 그죠? 고우시 인터랙션 처음에 했던 것과 마찬가지로 이제 본질적으로 같은 스트릭 스트레인이 나타나게 되는데 두 쌍이니까 곱하기 2하면 대충 한 7.2 kJ per mole에 해당되는 디세빌라이징 효과가 있다. 1-3 diaxial interaction 그렇죠? Alright, and you can be perhaps more quantitative using this thermodynamic formula, right? You can calculate the degree to which, right, the two conforming state partition. You can perhaps calculate the equilibrium constant, right? And this is the library of the strain energy, the actual strain energy, right? For the substituent of the cyclohexane ring. But what you can perhaps calculate the ratio, or in other words, the equilibrium constant, and plug in, right, all this information, then you can calculate the ratio of the two conforming state. And these are the result. So perhaps you can practice by yourself, right? And this is the constant, and then numbers must be given in the table. So you can refer to the numbers and plug into the equation and calculate the equatorial versus actual ratio properly. 한번 연습 삼아 계산을 해보셔도 되겠죠. equilibrium constant 계산을 하시고 그것도 ratio가 이제 나오겠죠. And here's a trend, though, right? You can perhaps practice, right, calculation here. The methyl versus tert-butyl, right? You can calculate the equilibrium constant ratio, 18 versus 5,000, right? And from these you can generalize the following: the larger the substitute, the more the equatorial substitute conformance is favored. Right? This is quite intuitive. And you can also think about the dye-substituted case and compare, right? The left and right. And let me see. We still have 3 or 4 minutes. Yeah, so maybe you can do a little bit more. So this is the dye-substituted case, right? And 1,4 dimethyl cyclohexane. So you can imagine, right? Methyl just here and there. And there is a case, cis versus trans. Okay? So you need to know how to define cis and trans. First, for what you need to decide the side of the ring where the substance resides. Right? So in this case, methyl is occupying downside of the ring. Okay? This is up carbon sitting on the equatorial. That means this is a downside. What about this methyl? So this methyl is attached to this down carbon, and down axial means this is the downside. Okay? So they are sitting on the same side. Okay? That's why this is cis. Okay? Cis means on the side, on the same side, basically. What about this case? This is trans. Okay? You can identify the side of ring. Again, this is the downside. Okay? What about this methyl? This methyl is locating on the equatorial position on this down carbon. So equatorial on down carbon is the upside. Okay? So they are sitting on the opposite side, that's why this is trans. Okay? Trans means across a different side in other words. So cis and trans isomers, or this is called the geometric isomers. We'll learn about and define all the language or terminology for the isomer for the next chapter. For now, you can accept this cis-trans isomers or geometric isomer. These two are not conformation isomers. Okay? 이렇게 두 개는 conformation isomer가 아닙니다. 그렇죠? 링 플립 한다고 왼쪽에서 오른쪽이 되는 게 아니에요. 아까 얘기한 것처럼 링의 사이드는 하나의 링 구조가 define 되면 upside, downside는 그냥 define 되는 거예요. 시스는 이 메틸이 같은 사이드에 있는 거고 트랜스는 메틸이 두 개의 메틸이 다른 사이드에 있는 거죠. 그럼 링 플립 한다고 바뀔 수 있는 게 아니에요. 그렇죠? 이거는 애초에 conformation 아이소머가 아니라 geometric 아이소머 혹은 cis-trans 아이소머입니다. Right, so that is about the cis-trans isomer, and I guess the next time we can maybe compare the energetics of cis versus trans isomer. So for each, you can think about most stable conforming state. Perhaps today or for the next class, you can practice how to draw the ring-fold version of the conforming state for each, and compare which one is more stable. 네, 오늘 여기까지 하고 다음 시간에 이어서 하겠습니다.